The example that they were giving of this is this notion of what's called the floating balloon graph. Okay, and the floating balloon graph is one of these things where, like, the higher something is rated, the higher the bubble goes. Does that make sense? And then what you can do is you could also make the bubbles like, so let's say the more valid something is as far as like a homeopathic remedy, the higher it goes. And then, like, the more times somebody Googles that as a potential homeopathic remedy would be like a bigger bubble. Does that make sense? So that already visual is way more like useful than trying to just list out all that information. But then what you could do is you could make it so that when the person opens the page, the bubbles start appearing in an animated way. So it catches your amygdala and says, ooh, it's like the bee flying in the room. When you animate it, they go, oh, I can see that. That's going to kill me, or it's going to make me feel better. It's not, I'm not sure which one, but I should pay attention to it because it's moving. And then the third thing that they could do is they could put like a little sidebar here with checkboxes for like what you're looking for a homeopathic remedy for, like heart problems or looking for headaches or whatever. And then you could check the ones that you want, and then the balloons change size and fade and whatnot according to the ones that you check. And the argument is that we're coming into the place in time and age where when you go to your boss, rather than handing him a data table, you're probably at some point, in order to make your case for something, you're probably going to hand him a tablet and say, here, play with this. And now this begs the question, like, what type of skills do you need to make that data realization happen? And like animation skills. These are all different things that are important all of a sudden. But the argument that I started making here was about this. And it gets interesting because you are living in a day and age where at any given point in time, you may be immersed into multiple realities. There is the reality of the room that you're existing in right now. If you were a student who's living or working remotely, there would be the room that you're in, and then the classroom that you're attending is a second immersive reality. And if you're shopping online while you're learning virtually in your room is one reality, the classroom is a second reality, and the online shopping that's now showing you the pretty thing that they want you to see, and you're flipping through pictures and animations, is now immersing you into third reality. And if you've got an Instagram feed coming up at the same time with somebody who's doing an Instagram story, you now have shopping, Instagram story, classroom, and actual space as all of the realities. And the way that your brain is hardwired is the actual physical reality is the one that probably feels least real. Because it doesn't have animation. It doesn't have all the motion. It doesn't have all the imaging. It's not actually hacked into your brain to make your brain pay attention to it. If that makes sense. So that was like the first one that I hit today, was like what reality is real and how immersed you have to be before your brain actually believes that it's real as opposed to the other realities. That came from data stuff. And then the second one that we hit today was in AP Stats. We were talking about chi-squared. Have any of you ever hit chi-squared in any of your classes yet? Where do you hit it? Bio, all right? Yeah. So bio asks this question. So, like, most people understand, like, the Gregor Mendel, I don't know, Brown recessant, sorry, oops. brown recessant should get you brown, 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 blonde, right? That kind of thinking. And that means that if you take a brown recessant and a brown recessant, then we should expect somewhere approximately 25% blonde in the phenotype, and you should expect approximately 75% brown in the phenotype, right? And what chi-square does is it says, okay, let's take a sample of like the offspring that actually came out, and let's say it was, 257 and 781, and these are the actual results, and compares these two things to each other using a chi-squared goodness of fit test, and then we get an alpha significance back, and if alpha is like less than 0.05, we go, hey, the model fits. Okay? And the problem is that this whole image is slightly outdated because this is like Gregor Mendel, ancient monk, kind of moving pea plants with each other. And this isn't how we do genetic testing anymore. We don't do it this way. How do we actually do genetics right now to actually come up with this stuff? How does it actually happen? Yeah, we're in the 23andMe space, right? It's exactly it. I go to mommy, right, and I take her DNA, and I take daddy's DNA, and then I run CRISPR on it all, and I say, okay, then what I would expect is that the kids would look like this. And then I look at the kids and go, did they look like that? And I go, oh, does chi-squared say that the kids look like that? No, sure it does. Amazing. And that got us to a really creepy place when we were in AP stats today, because the question was, what happens if you take 23andMe and combine that with like eHarmony? And is that our future? eHarmony is the dating site, right? So hey, you submit your DNA, all potential mates submit their DNA, and then we show you potential patterns for your children. I don't think we're far from that. Ooh. It depends if you're willing to wipe out certain forms of children. Yeah, we're kind of there. I'm not advocating for this by any stretch of the imagination, but all I could say is that these are two very profitable companies in our marketplace right now. And if these two things ever merge and become one company, that's going to be fascinating. Yes, it brings up ethical questions. I'm just here to posit that these are the ethical questions that you may be dealing with in your lifetime, and not too far down the road. There you go. Yeah. People donate eggs, donate sperm, yeah. Yep. And if they put a genetic profile with that, and you match your genetic profile to it, you get probabilistic models that could come out for children. Whoa. And then, is there a selection? Is there an unnatural selection that's going on there? And so these are the weird places that I hit in my life today in teaching. So, I know, fascinating, right? So, let's go after inverse matrices. So you saw this video on inverse matrices, I'm hoping. And inverse matrices are like one of the big questions, okay? And invertibility is really important. So what's going to happen in this course is you're going to find a list of what we call equivalent conditions. Okay? And it's going to be an ever-growing list of things that are all equivalent. Okay? When we get lists of equivalent conditions in mathematics, we like them. Okay? Because it's like a traffic circle. Like you can come into this traffic circle and then go out a totally different route because this is where things all intersect at one point. So we're going to get the idea here that A is invertible to being the same that A times some vector x is equal to some vector b has a solution. Okay, so what does this mean? If the matrix has an inverse, then the system of equations that corresponds to that matrix has a solution. Okay, and that's kind of fascinating. Now, what we're going to do is we're going to keep building on this list. That there's going to be a whole bunch of things that all mean the same thing that don't look like each other. Okay? And you're going to see this thread getting longer and longer and longer. Like, how do I prove that two things are, a matrix is invertible? And then that means that the system has a solution, and that means this, and that means this. And one of the things that linear algebra does is it finds all the things that kind of like come together at this convergence point. So convergence points are important. I'm just telling you that there is one here. Now, if I have a 2 by 2 inverse matrix, finding the inverse for that matrix is really easy if you do it by hand, okay? So if you look back, I think I had that in the notes, I'm hoping. Yeah. Did I put it in there? Yeah, there it is. Okay, calculating inverses. This guy. That 1 over AD minus BC, you switch the A and D, and you make the B and C negative. Okay, so what did I just say? If I have this, this matrix right here, right? All right, so it's A times D minus B times C, right? Switch the A and the D, make the B and the C negative. That will get me a inverse for a 2 by 2 matrix. Knowing how to do that is something you need to know how to do. Do I want you to have to know how to do this for 3 by 3s or 4 by 4s, so forth and so on, by hand? I'm not so worried about that. Okay, this is the base case for a recursive process to get you to 2 by 2s and 3 by 3s, and it's kind of crazy. But like, if this matrix was 1, 2, 3, 4, right? Does that make sense? Then I go 1 times 4 is 4, 3 times 2 is 6. I switch the 1 and the 4, and I make the 2 and the 3 negative, right? So this is going to give me 1 over negative 2 times 4, negative 2, negative 3, 1 gives me negative 2, negative 1, or sorry, negative 2, 1. That's going to be positive 1. 3 halves, negative 1 half. Should be the inverse for that matrix. Okay? That's how I deal with a 2 by 2. Knowing how to do that, that's pretty reasonable. I will admit I probably do most 2 by 2s by hand rather than load them into MATLAB because it's kind of fast. Now, here's the key. One really important thing. What happens if AD minus BC is equal to 0 here? There's no inverse. Because what happens? I get division by 0. Okay, that's a key point. And that is going to become like really, really critical. So like in the 2 by 2 case, AD minus BC cannot equal 0. If it does, then I don't have an inverse. Now, if you think about those things that I just said are equivalent, right? In the 2 by 2 case, A has an inverse. AX equals B can be solved, right? And AD minus BC equals 0, or is not equal to 0, are all equivalent statements. Because it's the only way you're not going to get an inverse with a 2 by 2. Now, let's talk a little bit about what does MATLAB do when you have a non-invertible matrix. So let's look at what would be a really easy non-invertible matrix. 1, 2, let's make it something more fun. 1, 6, 2, 3 should not have an inverse. 1 times 6 is 6, minus 2 times 3 is 6, which is 0, right? So that one should not have an inverse. And I should have started this before I started class. It'll get there. There it goes. All right, so maybe. Okay, so the first one I did was what? Was 1, 2, 3, 4, right? 1, 2, 3, 4 does work. So if I put in A, one, 2, 3, 4, right? And the keyword for inverse is INV, okay? It's just INVA. And it came back with -2, 1, or 3/2, -1/2. Exactly what I expect. And remember, you can always rats this and get the fractions. Oops, rats, not A. Rats, A inverse. Inverse of A. Yes, I can do that. There we go. But I can get the fractions there. But I also said, let's say B was, what did I say? It was 1, 3, 2, 6, right? I think was what I got. And then if you try to take the inverse of B, it yells at you. And it says, warning, matrix is singular to working precision. Okay, so this is MATLAB's way of hedging. Okay, it's saying, I don't think this matrix has an inverse, but I'm only good to 16 decimal places. So don't take my word on it. Okay, for our purposes, if it throws that warning, it's telling you it's not invertible. Okay, does that make sense? So when it gives you that warning, that word singular means that it doesn't have an inverse, and it sounds like a really weird way of saying that, but a matrix and its inverse forms a pair. A matrix without an inverse doesn't form a pair, therefore it is singular. So this matrix B, 1, 3, 2, 6, doesn't have a pair. Okay, so it is a singular matrix. Now, there's a couple of ways to actually work out how to find matrices beyond the second size. And like, you could go through and do like some pretty wild stuff here. Like, you get into this idea that you get like co-matrices. So like if I had 1, 2, 3, 6, -5, 1, 4, 2, 1, what you could do is you could pick like the first row, and then what you do is you take this number 1 and you find the determinant of the piece that's not in that row or column. Or sorry, you find this weird kind of thing that's going on here, and this is going to get like really exhausting. Okay, the easiest way to envision finding the inverse is actually to do this. to build a weird matrix that has the identity on this side and then put the matrix on this side. And if you take RREF of this, so this is RREF of identity 3 times matrix A, that's going to yield A times identity 3, or A inverse times identity 3. It's actually, I think I have that backwards. I'm sorry. The A should, these are backwards. Should be the other way around. Should give me, so sorry, let me rewrite that because I'm not making sense. If I took the matrix 1, 2, 3, 6, negative 5, 1, 4, 2, 1, and then put the identity over here, and RREF that, this is going to go from A identity 3 to identity 3 A inverse. So kind of playing that out, let's get the numbers that are here. Hopefully this thing is not singular. If it is, I'm sorry. So I have A being 1, 2, 3, 1, 0, 0, 6, negative 5, 1, 0, 1, 0, 4, 2, 1, 0, 0, 1, RREF A, and then it made it like weird. Let me just make it not so weird. There it is. So it's telling me that that is the inverse, the part on the right there. I'm going to rats the answer because it's hard to read that. There we go. So you would have never guessed that on your own. Okay. Now, fortunately for us, the algorithm that we just did there, like throw the matrix in, put it into Gauss-Jordan with the appropriate size identity, all I have to do is inverse A. Oops. Oh, duh. Without the other junk. So let's make B, just the parts that don't have the junk. Let me put A in there again. All right, so B will be the 1, 2, 3, 6, negative 5, 1, 4, 2, 1. Okay, so if I RREF A, right, and I take inverse B, the results are the same. So that whole algorithm is already built in, okay? Now, something to realize is that computing inverses for the machine is actually kind of labor intensive. It's not the easiest thing in the world to do, but it does it quickly because it's very fast. All right, so the other thing that can be visualized is this, and this is another visualization of the system of equations. So this is something to think about. Like if I had the system of equations, let's say 4x1 plus 2x2 plus 3x3 equals x1 minus 2x2 plus 5x3 equals, and then let's make this 7x1 minus 8x2 plus 4x3. And I'm going to make my answer 1, negative 1, 2. Can I do that? So if I put, that's going to be 4 minus 2 is 2, plus 6 is 8, right? 1 plus 2 is 3, plus 10 is 13. 7 plus 8 is 15, plus 8 is 23, right? I think. So this system of equations, in theory, should yield that result, I think. I just built it backwards. So what we're going to visualize this is we're going to make this matrix 4, 2, 3, 1, negative 2, 5, 7, negative 8, 4 times x1, x2, x3 is going to be equal to 8, 13, 23. See what I'm doing there? Making sense? Okay. This is the A matrix. This is my x vector. This is B, right? So if A times x is equal to B, if I multiply both sides by A inverse, then x should be A inverse B. Okay? With me? So let's play this off of MATLAB. We're going to put A in there as, let's clear this all out. We're going to put A in there as 4, 2, 3, 1, negative 2, 5, 7, negative 8, 4. And then we're going to put B in there as 8, 13, 23 as a column, right? So if I take the inverse of A times B, I get back the 1, negative 1, 2 that I expect is the answer. So there's an algebra going on here. Now, here's the big question. If I already know Gauss-Jordan, right, so why not just do C equals 4, 2, 3, 8, 1, negative 2, 5, 13, 7, negative 8, 4. Sorry, I'm getting in your way there. I moved me. All right, 7, negative 8, 4, right? 23. And RREFC and get the same answer. Why even mess with the inverse at all, right? And here's what's happening in the world of what's it called? Applied mathematics. This is what's going on. Is that this matrix in the problem is describing some condition of the world, which is kind of immutable. Like this matrix describes, like, you know, whatever it is about the world that I'm measuring that is immutable. This is describing the desired result, so the desired output, which means I'm trying to figure out, given the condition of the world, what is the input I need to get to the desired output? That's what a system of equations basically asks. Given the world, if I want this output, what input do I have to put in? How do I have to move the knobs in order to get the needle to land where I want it to? Now, the world is basically in this problem considered as an immutable for all intents and purposes. The desired outputs sometimes change, right? So like, one day I might want my school to have like vast diversity, and then the next day I might want my school to have like a great STEM focus, or the next day I might want but the world's not changing in which I'm building my school out of. Does that make sense? Or I'm working at a company and like currently this item is selling at a higher price than this one. So I want to sell 8 of these, 13 of these, and 23 of these. But next week I might want to sell 23 of these, 8 of these, and 5 of those. So what do I have to do is inputs on the other end. So this changes in the visualization. The matrix itself, the world, doesn't. Well, computationally, if I set this up in Gauss-Jordan, every time I run the computation, I have to have the computer go through the whole Gauss-Jordan iteration again. Whereas if the world is immutable, so is its inverse. So once I find, so A is this, right? Once I find, let's call it A2. Once I find the inverse of A, I don't need to recalculate that every time. I now have a tool. You can change B to be whatever outcome you want. So let's say I want B now to have the outcome 19, 14, 21, semicolons in there, right? What inputs do I need to get 19, 14, 21 out of this matrix? Well, I just take my inverse and multiply it by the B, and there's the inputs. So, oh, wait, I didn't mean 19, I meant 9, sorry. Well, okay, no problem. There's the inputs. And now I've reduced what's Gauss-Jordan. Think about how heavy Gauss-Jordan is. How many manipulations do you have to do to make Gauss-Jordan happen? Row operation, row operation, row operation, row operation, row operation, right? It's what we call polynomial time. Whereas now I've reduced that to one matrix multiplication. So I've done the polynomial time once to find the inverse, but now that I have it, I just do one matrix multiplication, which is linear time. And I've sped up the process computationally a lot. So remember, accuracy, so I attain the same accuracy, but speed is now the goal. I get much more fast computational speed. Computational speed is not going to matter when the world is described by a 3x3 matrix. Computational speed is going to matter when the world is described by a 100,000 by 100,000 matrix. Okay, it's going to matter a lot. All right, so this gives you, hopefully, some of the drive behind the problems that I'm asking about here. So if you go to the inverse matrix problems, right? 1, 2, 3, 4, that's just plug it into MATLAB and get an answer, right? Now here's what's going to freak you out. I know that matrix 3 does not have an inverse just by looking at it. I know that matrix 4 does just by looking at it. And now the question in number 5 is, how did he do that? And is there a trick? And the answer is there is. Okay. 6 is another, can you find the inverse quickly? Okay. And 6 is interesting because the first and third row are the same and the second and fourth row are the same. Oh, okay. 7 and 8 are, can you do this with a system of equations like I did, using the A inverse and the B? And then it asks you to do some manipulation to see if you can figure out what's going on with rules there. Okay? And then 13 is interesting because you got to do it by hand, right? Let's just play 13 for a moment. Can we just do this? So the question is find X so that the matrix is itself, right? I find this a particularly interesting question. So that's one that you're likely to get stumped on a little bit. So remember, A is this. A is 3x negative 2 negative 3, right? So the inverse should be 1 over, well, what's 3 times negative 3? Negative 9. And then negative 2 times x, so that's going to be plus 2x, right? And then we switch the 3 and the negative 3. So it's going to be negative 3 and 3. And then we change the signs of these. Correct? All right, so what do I get? I get some weirdness here. I get negative 3 over negative 9 plus 2x. Okay. I get x over negative 9 plus 2x. I get negative 2 over negative 9 plus 2x. And then I get 3 over negative 9 plus 2x, right? But do I need all four to solve this problem? Do I need to find x for all four of them? Because the x is the same in all four, right? So why not just take like the upper left-hand corner and say, what happens if I go negative 3 is negative 9 plus 2x is equal to 3? Right? So cross multiply. Negative 3 is negative 27 plus 6x, I think. Probably. Shouldn't have done that, but it'll work. Divide it all by 3. Negative 1 is negative 9 plus 2x. That makes more sense. Right? 10. Let's see. No, that's going to be 8, right? 8 is equal to 2x, which means x is equal to 4. So my conjecture here is that if I make it 3, 4, negative 2, negative 3, this should work. How do I test? Put it into MATLAB, maybe? So what do I got? I have A is 3, 4, negative 2, negative 3. And if I take the inverse of A, I get itself. Huh. Do you think there's something special about that matrix? And do you think there are a lot of matrices that have their own inverse? And do you think those would be useful? Kind of interesting. So why did I only need one of them? Because if it works for one of them, it's going to work for all of them. Does that make sense? Otherwise, the thing's not invertible, and then I have a problem. And then I have division by 0. The division by 0 would be only happening if it was 9/2, which would be bad. 15 is also an interesting question. So, like, oh, my hard drive's almost full. How about that? I don't think that's true, but we'll figure it out. Oh, it's because I'm recording. So let's talk about, like, what would you do there? This is saying that the inverse of this should be the same regardless of the theta, right? Anybody see why it's going to work? Okay. Try taking the inverse of it. If I have sine theta, cosine theta, negative cosine theta, sine theta, and I want to take the inverse of that, this becomes 1 over what? Yes. Now, oh, right. Sine times sine is sine squared theta, right? Minus negative cosine squared theta is plus cosine squared theta. And then what goes on the inside here? The two sines are supposed to switch places. So that's not going to happen. And the cosines become negative. And that, you just told me, is 1. See the interesting bit with that one. So the inverse of sine, cosine, negative cosine, sine is sine, negative cosine, cosine, sine. And believe it or not, I have that memorized. Because one makes a rotation this way, and then the other one makes the rotation back. So there's a thought. So like if you put, here's what it is if I put sine pi over 4 cosine pi over 4, negative cosine pi over 4, sine pi over 4, and I multiply that by the point, let's say 3, 4, that will rotate 3, 4, pi over 4 degrees around the origin. And then if I use the inverse, it rotates 3, 4, right, clockwise. So it's a rotation this way versus a rotation that way. So kind of interesting stuff there. All right, I'm going to be quiet, let you guys play for a while. Okay? So welcome to the world of linear algebra. How are you guys doing? Okay? Stuff's making sense? Cool. So as you're moving forward, just keep trying to like conceptualize, if that makes sense. Like if you're seeing things like patterns in the matrices or things like that, because like there's definitely a pattern to like the one in number 6, number 4, and number 3. Like there should be something you should notice about them. I don't know if you do or not. But we'll show you where it is as we go forward, if that makes sense. Okay? Can we call it a day? Awesome. Very good.